All right, we are now recording. Let me start with the announcements. I think I've told you before, probably many times, that the college transfer fair days are coming up starting 2 weeks from today. The first of the Birmingham campus, Birmingham West campus, on Wednesday, February 12th, exactly 2 weeks from today, 9:30 to 11:30 in the morning. That's on the in the academic building. That's B Hall on the Birmingham West campus. I imagine the tables will be all up and down that hall, and the various universities and colleges will be there. Then on Thursday, 1 week from 2 weeks from tomorrow, they'll be on this campus, February 13th, 2020, and that will be 9:30 to 11:30. Now they say on this campus, in this building, they say in the campus cafeteria, I'm guessing in the faculty staff dining room, which is right next to the campus cafeteria. I don't know for sure, but that would be my guess. That's a less used room than the cafeteria is, and certainly plenty of tables to be set up in there. They may spill into the cafeteria or the hallway, but I think they can get most everybody there. All right. Now, I was suspicious about this because the Thursday's the 15th, which would make Thursday's the 13th, that would make Saturday the 15th. And yet they had this thing, the deadline was February 15th. I thought that's odd for them to have that on a Saturday. Then in the brochure, I noticed they had moved it to the 17th, which would be the following Monday. Now, I don't know which of those dates are correct. I assume this one is, but just because I would doubt if they'd have it on a Saturday. But anyway, that's that summer research program. Now, there's a bunch of them out there. This one sounds like it's geared more for engineering, specifically mechanical, electrical, material, but I know there's other of these research opportunities for undergraduates out there. And let's see, that's all I know about so far. Let's move on to any questions on anything we've covered so far. Okay. Now, my memory is we had done this slide, I'm pretty sure. No, maybe not. Yeah, we had done this slide. And we're getting ready for the next. Is that where you remember, or? Okay. So.
Yeah, this is where we were.
Yeah. That's what came up. I thought we've already done that slide, or at least my memory was we did. All right, so here are some characteristics or properties or whatever of vectors in space. Okay? That U, now this U is not necessarily a unit vector, so remember that. U is any old vector, U1, U2, U3. Those are the three components of the vector notation. Okay, and V is V1, V2, V3. Vector components. Okay? The vectors in space, C be any scalar in the world. Okay? First, the equality of vectors. U is equal to V if and only if U1 is exactly the same as V1, U2 is exactly the same as V2, and U3 is exactly the same as V3. The only way two vectors can be equal. Doesn't mean their magnitudes are equal. Any two vectors can have equal magnitude, be pointed in totally different directions. They have to be identical. The components must be identical. Now, component form. If V is represented by the directed line segment from P, now this is a point, P, which is P1, P2, P3, these are coordinates of this point P, to Q, from P to Q, Q is Q1, Q2, Q3, coordinates of the point Q, and here's Nelson. And Fred snuck in too. Okay. And he's sneaking out again. Okay. So we're doing this where we left off last time. V is represented by a directed line segment from point P to point Q, where these are coordinates of those points. Then the component form for V, V1 would have to be Q1 minus P1, V2 would have to be Q2 minus P2, and V3 would have to be Q3 minus P3. Okay? Component form. The length of a vector V would be the magnitude of, or the length of, that's length or magnitude of, is the square root of V1 squared plus V2 squared with V3 squared. So that's vector V, that's how you find this length. A unit vector in the direction of V, just like we defined in space, in two-dimensional vectors in the plane, the unit vector in the direction of V would be the vector V divided by its magnitude. That would give you a magnitude of 1, making a unit vector in the same direction of V. So, another way to write this, instead of V, write it in component form. V1, V2, V3, components divided by the magnitude of V. In fact, you'll see it that way a lot. Actually, I would take it one more step. The component of V1 over magnitude of V, comma V2 over magnitude of V, comma V3 over magnitude of V. That's how you would see it. Now that is true as long as V is not the zero vector. And that should be a, yeah, I guess it is a bold zero. The zero vector, because it has no magnitude, the magnitude would be 0, you can't divide by that, and it says a unit vector in the direction of V. The zero vector has no direction, so how, this makes no sense. All right, vector addition. You have vectors V and U as defined above, then the sum of those two vectors is the vector V1 plus U1, comma V2 plus U2, comma V3 plus U3. Why they put V plus U here? Yeah, okay, they get it right. Now, scalar multiplication, C, that's vector, that's scalar, C, multiply vector V would be CV1 plus comma CV2, comma CV3. Okay. Pretty simple, straightforward. Characteristics of vectors, I guess you would say. Goodness, I'm cold in here. All right, let's see if they have example 3. They do. Not only do they have it on the slide set, they also have it at larsoncalculus.com. There you can see an interactive version of this type of example worked out. Okay? Now, find the component form and the magnitude of vector V having initial point -2, 3, 1, terminal point 0, -4, 4. Then find the unit vector in the direction of V. How would you begin? First they want component form, then they want the magnitude of the vector V. Let me get my pen set up. Boy, it's cold. What would vector V be? Says first component form. Give it to me. Anybody? Say again?
So, component form is where you take the terminal points,
Right.
subtract them by the initial point.
Yep.
So the first one is -2.
This minus that 2.
-1.
negative
-7.
-7,
And
3. Okay. There is the component form of it. Now just give the magnitude of it. What would that be? Second,
it's the square root
square root of
of all of those numbers squared.
okay,
2 squared,
4
4 plus 49
plus 49 plus 9, and that would be the square root of 58 and 4, 62. I did it in my head. I don't know if it's right. Now, usually when you have radicals like this, you see if there are any hidden lurking perfect squares in there. I don't see any. That would be 2 times 31. 31 is a prime number. 2 is a prime number. So nope, nothing there. Now, then it says find the unit vector in the direction of V. Okay, and I'm going to write this as unit vector in direction of V. That's going to be my notation for it. What would that be? Basically, they've really set you up nicely for this. They've given you the pieces, just put them together.
Is it the vector V of the magnitude?
Right, which would be 2 over root 62, negative 7 over root 62, 3 over root 62. Now, fairly, maybe not easy, but reasonable to check and see if that is indeed a unit vector. We sort of know it's got to be in the direction of that, okay, because it's the scalar 1 over root 62 times that, so it has to be in that same direction. And if you square this, you get 4 plus 49 plus 3, plus 9, 62. Got to be. So, that's how we did it. Let's see how they did it. So I think I'm going to have to erase this. Any questions before I erase it? Okay. So the component form is the, like you said, terminal minus initial for each component. And they spelled it out there for you, and it gave you 2, negative 7, 3. All right. Magnitude of that then would be the square root of 2 squared plus negative 7 squared plus 3 squared, which is root 62. Okay? Leaving Chicago. Never mind. Okay? And then to get the unit vector in the same direction of V, just merely take V, divide by its magnitude, and here they used U as a unit vector. It's not always. I want to just remind you of that. Don't think anytime you see a vector U, it's going to be a unit vector. This one will be because of that definition there. And this will be, they put the 1 over root 62 in front times the vector root 2, negative 7, 3. And then they write it the way we did. 2 over root 62 minus 7 over root 63 to 3 over root 62. Any questions? Pretty straightforward, right? Okay. Now, top of page 765, recall that from the definition of a scalar multiplication, that positive scalar multiples, okay, of a non-zero vector V have the same direction of V, whereas negative multiples have the direction exactly the opposite of v. In general, two non-zero vectors u and v are parallel when there is some scalar c such that u is equal to c times v. And that c can be positive, negative, not zero, okay, some scalar other than zero. I should have said that, some non-zero scalar c such that u is equal to c times v. And c could be positive, negative, fraction, decimal, rational, irrational, it doesn't matter. Tiny, huge, positive or negative. So here's the definition of two parallel vectors. Two non-zero vectors u and v are parallel when there is some scalar, some non-zero scalar c such that u is equal to cv. Well, I guess you don't have some to say some non-scalar. Up here, I think you do. Okay, maybe not. Because you see, well, I still think you do. Because if this is some vector v, okay, and multiply it by 0, you get that. You can't say those are parallel unless you say 0 vector is parallel to any vector. And that's a little bizarre. I don't think that would make sense. Okay, but that's a minor point. For example, in this figure here, hold vectors u, v, and w are all parallel because u looks like it's exactly twice v, and w is equal to exactly minus v. So this has a scalar 2, has a scalar -1. So those are indeed all parallel vectors. Any multiple in the same or opposite direction would be parallel. All right. Example 4 is next. Vector w. Goodness gracious. You took your jacket off. Okay. Can I borrow it? No, I'm just kidding. Okay. I need gloves is what I need. Vector w has initial point 2, -3, -1, 3. Notice that's parentheses, so they mean coordinates of a point, terminal point -4, 7, 5. Okay? Which of the following vectors is parallel to w? So what you reckon we ought to do first? Second? Yes. Get w in component form, and what would that be? -6, comma. Be what? 8. Okay, I just can't hear well. Okay. 2. Okay. Now, which of these two vectors is parallel to that one? Think you might be? Yay or nay?
Yay.
Second? Yay. Okay. Yay. All right. Got it right. Okay. Because, and you can say it either way you want to, u is equal to -1/2 w, or you could have said w is equal to -2u. Either one of those would work. How about v? B, which is v. Okay, never mind. What would that be? Yay or nay? Yes? Say again? Why not? Is it?
It looks like it's times -2, but for the first two, but it wouldn't work.
Wouldn't work for the next one because, and probably isn't how they recommend doing it, but I noticed the signs are plus minus minus. So to be parallel, they've either got to be plus minus minus or minus plus plus. Okay? And this is plus minus plus, no way. Even though the numbers are doubled exactly, the absolute values are, the signs can't be correct. Because they either got to be the same order or exactly the opposite order and size. So yes, the first one is, second one, no. Okay. Let's see if, that is a little bit in the way, so I'll erase it. All right. Begin by writing W in component form. You're absolutely right. We did it. And because U is exactly negative 1/2 of W, it is parallel. But in the B case, you want to find the scalar C such that that's true. And as you said, when C was -2, it worked. But it did not work for the third component, because that was C equal +2. And I believe Ryan never showed up today. Okay. And Josh's still out of town, is that right? All right. So even though -2 works for the first two components, third component is a multiple of +2, not -2. They all have to be the same. All right, any questions on that? We just finished example 4, page 765. So let's see if they do example, oh wait. This means that the equation 12, vector 12, -16, 4 equal to C times -6, 8, 2 has no solution. The vectors are not parallel. Whoa, no, they do not do example 5. So let's us do example 5. Bottom of page 765. Determine whether the points P, which are 1, -2, 3, Q, which is whose coordinates are 2, 1, 0, and R, which is 4, 7, -6. Ooh, that's ugly parentheses, isn't it? Okay. Determine whether those points are collinear. Well, what does collinear mean anyway? What you reckon it means?
So like they're all on the same line?
All on the same line. Okay? Now, what would indicate that would be the case?
Typically, same slope.
Okay, same slope. That's one way of phrasing it. And yes, they would all have to be parallel. Okay, that's based on what we were just doing. That would give us the answer. So what might be a technique for determining if these are collinear? Okay, which one? P and Q. So let's first look at vector PQ, and when we write it this way, put the initial point, it doesn't matter which one you use, but we'll use P under the initial point there and the terminal point under the tip there. And what would that be in component form? Which is 1, comma, which is 3. Is that what I heard? Okay. -3. Okay. There's vector PQ. what you want to do next. QR would be perfectly fine. PR would be perfectly fine. Okay? Either one, because if these two are parallel, they all have to be on the same. You say QR, so let's do that one. And what would that be? 2, okay. 6, -6. What can you conclude there?
It's double.
Second?
All points are double.
Yes, exactly doubled. And so that, what are you able to conclude from that? Yes.
I have a question. How did you determine QR?
QR?
You did 2 minus 4, or did you do?
Okay.
4
You always put the initial point under the initial point of that arrow and the terminal point under the tip of the arrow. Initial terminal. Okay?
So how,
And then you do final minus initial. Terminal minus initial. Now, yeah. So 4 minus 2, 2. 5, 7 minus 1, 6. -6 minus 0, -6. Okay? And then y'all said that that was double. What does that tell you? They are parallel. And if the 2 points are parallel, and they have 1 point in common, 2 lines, vectors are parallel, 1 point in common, they have to be collinear. Okay? And that would have worked if you had done it PR. Is there another combination? I don't really think so. Or reverse them, RQ or RP or P, whatever. It would have still worked. And let's see what they concluded here. They did PQ and PR. They also found if they have 1 point in common, which obviously they both do, if they're multiples of each other, they are collinear. They're parallel, which means they're collinear. Okay. I think, didn't I just find out this previous one was the last slide? So let's do example 6. Any questions so far? No. The A part of 6 is write this vector V equal to 4I minus 5K in component form. What would that be? Back when I was growing up, that was component form, okay? We didn't have the angle bracket. That's what they're looking for here. What would this be in component form with angle brackets? Four, 0, you said? Yes, 4, 0, -5. Perfect. Okay, everybody see why that's true? Those are the components. It's just you don't have a J component, so you put a 0 in for that. All right. Question? Oh, okay. The B part. Find the terminal point of the vector V. This is a different V, I'm pretty sure. I'm certain it is now. 7I minus J plus 3K, given that the initial point, and they're going to call it P, is -2, 3, 5. These are coordinates of a point. Those are, these are coordinates of a point. Those are coordinates No. Components of a vector. Coordinates of a point, in parentheses, components of a vector, either in angle brackets or IJK notation. Okay? How would you find the terminal point? Anyone have a choice or preference on what we'll name that terminal point? Oh, I never saw that coming. Okay. And that's going to be, let's just call it Q1, Q2, Q3. I can't write. Okay. What would be the coordinates, because this is a point, of that terminal point?
You subtracted the P minus the vector, would you get Q?
Okay. Let's see. I would just write this down first. You don't have to. You're probably thinking correctly. V is equal to Q1 minus or plus 2. You okay with that? Q2 minus 3, Q3 minus 5, right? And then, now that I think about it, I wouldn't write V. I think I would write that as, in component form, what would that be? 7, negative 1, 3. Okay. Now let's see if what you were saying is what I'm understanding. Q1 would be, I think it's what you said, 5. 7 minus 2, that would be 5. Q2 would be, okay, you're subtracting that which is adding, right? 2. And, well, I wrote 2, but nothing happened except my screen went black. And everything else showed up. So let's try this again. Why is this not writing? It's lost its mind. Okay. I'm afraid if I cancel this out, I'll lose my whole PowerPoint. So let me, what do I do? Let's go from current slide. Okay. I don't know what it did, but anyway, let's go. What did you say this would be? 2. There it wrote it. Okay. And Q3 would be, second, I think that's a 3, isn't it? That's a 5. 8. So this suggests that point Q would be parentheses, because it's a point, 5, 2, 8. All right. Now, the way to check this is 5 minus a minus 2, that would be 7. Yes, yes, yes. 2 minus 3 would be minus 1. Yes. And 8 minus 5, 3. Yes. I believe that's it. And what they got was Q1 is 5, Q2 is 2, and Q3 is 8. Good for them. So the point Q is 5, 2, 8. Good for them. All right. Now, I have another little ditty for you, so let's erase what we've got here and do the C part. This is, I think it's 6C, isn't it? Yeah. Find the magnitude of this vector. V is equal to negative 6I plus 2J minus 3K. Then find the unit vector in the direction of that vector V. So the first part said find the magnitude. That's written as magnitude of V. What would that be? Anybody? Okay, was he say square root? Okay, of, which is 36 plus 4 plus 9. Okay, that's going to be not too bad a math. Anybody?
49.
Square root of 49, which is 7. There's the magnitude of V. Now, is that plus or minus 7? I don't remember. Only positive, yeah. Magnitudes are always positive. Okay? So that's the first part. Find the magnitude. Done. Then find a unit vector in the direction of V. So I'll do as the book has done. Call it U, but I'm going to put a caret on top, understanding that is a unit vector that's in the direction of V. What would that be?
V over magnitude.
Say again?
Is that the V over magnitude of V?
No, it's the unit vector in the direction of V. That's not, I made up this notation. This isn't in the book. Okay? But the unit vector in the direction of V. I should have put, say again? Negative 6 over 7. Are you writing this? I can't write at all. Okay? Goodness gracious. Now, are you writing this in?
With the I.
Okay, you're using the IJK notation, okay? Negative 6/7 I
Plus 2 over 7.
2/7 J, if I could write, negative 3/7 K. Or you could have written in angle brackets, negative 6/7, comma, 2/7, comma, 3/7. Okay? Just no need really to do it because that's exactly how we got that. Right. Okay. And they wrote it this way too, in IJK notation. All right. Any questions on that? Well done. I feel pretty rare now, as cold as it is. Okay. No questions, so erase. Okay. And let's do example 7. Okay. I'm sorry? Okay. I'm sorry. I could have left it longer if you'd have said something. Example 7 is measuring force. And here we have a television camera weighing 120 pounds. Now, for those who haven't had your physics yet, that is a force unit, pounds. Is supported by a tripod. By the way, that's a pretty hefty TV camera, but some of them are pretty large. It's supported by a tripod, that means a 3-legged device, as shown in the figure here. Represent the force exerted on each leg of the tripod as a vector. Okay. I was hoping not to have to draw this, but I think I'm going to have to. Do all of you have either a book or a e-book, or
Yeah, we got this.
everybody has something to look at? You do too, Dawson? You got it up there. So what I'll just do is draw the points. The foot down here is Q1, and this is at 0, -1, 0. The foot over here, Q2, is at square root of 3 over 2, 1/2, 0. And the foot over here is at Q3, which would be -3/2, -√3 over 2. (1/2) and 0. All right. So the camera is hanging somewhere here, and its weight, which is always straight down, is 120 pounds. Okay. So we got one leg this way, one leg this way, and one leg that way. Okay. Now we want to know the force exerted on each leg of the tripod, and write that as a vector. Okay. Oh. Now, they also indicated here, sort of snuck it in on me, I wasn't really paying close attention to it, that the center of this is the origin. Okay? So the camera is directly over the origin, 0, 0, 0. Okay? You can see that by the z-axis coming through the top of the camera, and you can just barely see the z-axis almost hidden behind the line that connects Q2. Okay. Now, they also make the camera point P. Okay? Now, oh, and they actually gave coordinates for it. 0, 0, 4. Okay? That helps a lot. Okay? Now, if these are three forces, F1, F2, and F3. Now that they've done that, we can actually put arrows on this and indicate those are the three vectors. Okay? I think they named this one F1. Yeah. Vector. This one would be F2, a vector, and this would be F3, a vector. Okay. You know what? It looked like they were asking it to be a really difficult problem, but since they labeled all the points and told you these are the three forces, not at all hard to figure out what it is. What is F1? Force 1.
Initial point 0, 0, 4, terminal point 0, -1, 0.
Yeah. And what is the force which then is the from P to Q1? Second, 0. -1, isn't it? Yeah.
4,
-4. All right. Now, no, I take this back. This is the direction of F1. This is not F1 itself. this is the direction of F1, okay? So, kind of, in the book they're not specifying this, but let's continue. What's the direction? So I'm going to call this DIR, okay, and this is DIR of F2. What would that be? Again, pretty easy. Square root of 3 over 2, is that what you said? Yeah, I could say yes, okay. 1/2 and -4. Okay, and the direction of F3 would be negative root 3 over 2, comma, 1/2, comma, -4. Perfect. Okay. Now, these are the directions of, and they do say that, I hadn't read it in the book, these are directions of these three vectors. And because all three legs have the same length, we haven't determined that, but we could. What would be the length of one? Say again? No, just the length of one. Length of this vector here, which gives you the direction.
Magnitude.
Say again?
Take the magnitude of it.
So you do the square root of that thing squared. Sum of the squares. What would that be? Square root of 17. 1 plus 16. Yeah. 17. Okay, let's see if these come out the same. Okay? This would be 3/4 plus 1/4 plus 16. That's 3/4, 1/4 is 1. 17. That would be
Same thing.
same thing. Okay, yeah. So all three of those have the same length, these directional vectors, okay, which is encouraging. Okay, you set it up well. Now, in effect, that means that each of these forces, the magnitude of each of these forces has to be that isn't quite what it means. I was going to say would be 40 downward, okay? Because each of them is carrying 1/3 of this, because the lengths are the same, everything's the same. So what you do know is the magnitude of this needs to be 30, okay? And the magnitude of each of those has to be 30. I doubt if that's the way they're going to approach it, but it is. It's pretty close. And actually a sort of an easier way to do it. Just like I said, probably didn't quite say it right. the vertical component of each of these has to be 40. And since that is exactly 10, a negative 10 times, and negative being downward, 10 times this, 10 times this, 10 times this, you know those components have to be that way. So basically, the force vector itself is 10 times this vector. So that would be, F1 would be 10 times 0, 0, 10 times negative 1, okay, and 10 times negative 40, and negative 4 is negative 40. F2, five root 3, is that what you were saying? This would be 5, and this would be negative 40. This one, F3, would then be negative 40. Now, what we hope to happen is that the sum of these three vectors had better be negative 0, 0, negative 120, right? Well, that is the force vector down. So these two add to 0, and 0 is 0. This is negative 10 plus 5 plus 5. That adds to 0, and these three add to negative 120. And since negative is down, that makes sense. So those are our three force vectors. Sort of a strange kind of problem, but pretty interesting kind of how they did it. That direction vector is a little, it's true, but it's just seems a little bizarre way of doing it. Okay, that finishes 11.2. Any questions on 11.2? Okay, here's some practice on 11.2. Do either 5 or 7, they're both at Calc Chat. Either 9 or 11, they're both at Calc Chat. 9's at Calc View. Any of the odds 13 to 23, they're all at Calc Chat. 25 or 27, they're both at Calc Chat with 25 at Calc View. 29 or 31, both at Calc Chat. 33 or 35, both at Calc Chat, with 33 being at Calc View. Any of the odds 37 through 41, they're all at Calc Chat. 39's at Calc View. 43 or 45, both at Calc Chat. And 47 should be at Calc Chat. 49 should be at Calc Chat. 51 or 53, they're both at Calc Chat. 51's at Calc View. 55 should be at Calc Chat, and 57 should be at Calc Chat. Either where's my throat going? I don't know. 59 or 61, they should both be at Calc Chat. 63 or 65, both at Calc Chat. 63 is at Calc View. 67 or 69, both at Calc Chat. 67 at Calc View. 71 should be at Calc Chat. Goodness, my hands are cold. Any of the odds 73 to 77, they should be at Calc Chat. 79 or 81, both at Calc Chat. 79's at Calc View. 83 or 85, both at Calc Chat. 87's at Calc Chat. 89's at Calc Chat. They keep on coming. 91 and 93 are sort of writing exercises. If there's anything in there that would lead you to a research paper, you might consider it. I don't know what they have at Calc Chat, but they should be there. 95 and or 97 should be at Calc Chat. 99 should be at Calc Chat. 101 and or 103 should be at Calc Chat. Okay. I was thinking of something as I was assigning those, and I didn't want to stop, and now I forgot what I was thinking.
Was it something about the paper?
Well, I said that on the writing exercises. All right. If I think of it, I'll come back to it, but I don't recall now what it was. So let's move on to section 11.3. How are we doing? Oh, here I've got it, 129. And we go to,
210.
say again?
210.
210, yeah. No. Yeah. 210, yeah, and the next class starts at 2:30, that's right. Have 20 minutes on that one. All right. What I want to do is get out of this to go to 11.3. 11.3 is a very useful feature of vectors. Okay? So we're still in chapter 11, Vectors and Geometry of Space. 11.3 is going to be talking about the dot product of two vectors. Now, I know some of you have taken physics before. Maybe you've had this before. Do you know what we mean by dot products? Isn't that sort of redundant? Doesn't the center dot mean you take a product? Well, in vectors, there's two different kinds of products. Actually, there's sort of three. One we've already talked about, a scalar product, which means you multiply a scalar times a vector. That's pretty straightforward. But if you notice, we never said anything about multiplying two vectors together. Well, there's two ways to multiply vectors together. One of them is a dot product, because we use center dot to represent multiplication. The other is a cross product, because we also use a times sign, cross sign, to indicate multiplication. These are two completely different kinds of multiplication. So we're going to hit the dot product first. This is one way to multiply two vectors together. Scalar product is a scalar times a vector. This is one way to multiply two vectors together. All right. So, we'll use the properties of dot product of two vectors. In other words, we've got to figure out what they are and use them. In fact, we've got to figure out what a dot product is anyway. Then we'll find the angle between two vectors using a dot product. We'll find the direction cosine. Well, we first got to figure out what in the world that is, but then you find the direction cosines of a vector in space. Find the projection of a vector onto another vector. And we'll do that both in a plane and in space, I think. And we'll use vectors to find the work done by a constant force. Yeah. See if there are any others. No. Let's start with what in the world is a dot product. So, you've studied two operations with vectors. One is vector addition, which includes subtraction. Okay? And the other is multiplication of a vector by a scalar, each of which yields another vector. In this section, you'll study a third vector operation, the dot product. Now that product, however, yields a scalar, not a vector. Later, we'll do the cross product, and guess what that yields? A vector, not a scalar. Okay. So here's the definition of a dot product. You have, and this is one way to approach it, and it's a pretty nice way, the dot product of vector u, which this is in a plane, two dimension, u1, u2 are the components of u, and v has components v1, v2. Okay? Here is a definition of the dot product. Multiply these two components together. Now these are components, those are scalar numbers, and add to that product the product of U2 and V2. Okay? So it's U1, V1 plus U2, V2. And guess what? These are scalars, that's scalar, sum of two scalars is a scalar. Ooh. In space, or in 3 dimensions, and not too long from now, Dawson will be doing this in dimensions. You know, you can still do dot products this way, no matter how many dimensions you are. He's in linear algebra. It's U1, V1 plus the product of U2, V2 plus the product of U3, V3. And then if you had multiple dimensions, you just keep adding their components. Of course, both vectors have to be in the same space, in the same dimension. So that's what a dot product is. The sum of the products of the corresponding components. Okay. That's your definition of a dot product. Given that, let's look at the properties of these dot products. Now we have 3 vectors, u, v, and w, all vectors in the plane or in space, whichever you want them to be, but they all have to be in the same dimension, 2 or 3 dimensions. CV is scalar, just like before. Here's the commutative property of dot products. U dot v is the same as v dot u. Let's just use 2 space to begin with. Of course, this sort of makes sense. This is u1 v1 plus u2 v2. This is v1 u1 plus v2 u2. Guess what? Those are just scalars. It doesn't matter the order you do those. That's the commutative property. Dot products commute. You can do them in any order you want to get the same result. That will not be true of cross products. So hang it up for now. Okay, here's a distributive property. Okay, U dotted with the sum of V and W. So this would indicate you add these together. This would be V1 plus W1, comma, V2 plus W2, comma, V3 plus W3, or let's just keep it 2 dimensional. That makes it easier. Okay, and then you dot this with that. So that would be U1 V1 plus U1 W1 plus U2 V2 plus U2 W2, and that's exactly what you get here, U dot V plus U dot W. Okay? If you split those off, you would have that. So in dot products, distribute the product of the dot product of a vector times the sum of 2 other vectors distributes over the sum. So U dot V plus U dot W. This is a vector. Dot product produces a scalar. That's a scalar. That's a scalar. Sum of 2 scalars is a scalar. Okay, everything seems to make sense there, I hope. Okay? Number 3, when you have a scalar product of a dot product, a scalar times a dot product, well, this is just a scalar, isn't it? So you should just get a scalar number, and sure enough, that's what you're going to get. But this distributes also. No, this is an associative property. Sorry about that. Okay, you can do the C times the U and dot that with V, or you can do the U and associate the C with the V, but don't do it with both. C is multiplied just once by either of those. So this is either CU dot V or U dot CV. Okay. It's kind of an associative property. The scalar associates with either of the 2 vectors in the dot product. What's that?
Either or.
Yeah. Okay, yes, exactly. Now, if you dot the 0 vector with any other vector, you don't get the 0 vector, do you? Because you get a scalar, the number 0. Because this would be, if this is in 2 space, 0 times V1 plus 0 times V2, well, that's 0 plus 0 is 0. Okay. Now here's an interesting and a useful one. Now this doesn't have a name, so it's not quite the 0 property of scalar multiplication of dot products, but it's kind of like it, I guess. You would have to have some if-thens in there. We don't have those. V dot V is the magnitude of V squared. This is a scalar. Magnitude of V is a scalar. You square a scalar, you get a scalar. Those are the same values. Okay. Because this is V1 times V1 plus V2 times V2. Okay? Well, the square root of that would be the magnitude of that. So what I just said was the square of that magnitude. All right. So there's the properties of the dot product. They do in the book a little proof of one of those, and they do it in 3 dimensions. I think I basically just did it for you, the fifth one. Just talked through it same way. So let's do this one. U is a vector 2, negative 2, V is a vector 5, 8, and W is a vector negative 4, 3. All 3 of those are in a plane. Okay? So they all have the same dimension. What in the world is U dot V? Okay? Now, I wish they hadn't have done that for you, but they did. What would that be? Anybody?
2 times 5.
Okay, which is 10
Plus negative 2 times 8.
which is
Negative 16.
negative 16, and that is
Negative 6.
negative 6. Dot products can be negative. Nothing to keep them from being. They can be 0.
What about the U1 and U2 times U1 and U2?
Okay? That's what I think we just did.
It is.
This one does this. U1 times V1, that's 10, plus U2 times V2, that's negative 2 times 6, 8 is negative 16, so 10 minus 16 minus 6. Okay? All right. There's the A part. Let's see how they did it. Oh, can't see how they did it. Okay, 2 times 5 plus negative 2 times 8 is negative 6. Same way. All right, what's the B part? That's U dot V times W. Well, we just did U dot V, so we just brought down that minus 6. I wish they'd have let us do it. And we're going to dot that with, multiply that as a scalar multiplication times W, which is negative 4, 3. So what would this give us? 24, negative 18. But that is a vector, okay? Okay? This wasn't exactly one of our properties that we had before. They didn't do one like this.
That's association.
Second?
That's not association. That's not association.
No, it's... This produces a scalar, right? The dot product produces a scalar, and then this is just scalar multiplication. This is the scalar produced by dotting those two together, and then you do scalar multiplication times that other vector, and that's what you get. Okay? Now, they didn't do the math. We did the math. Let's see what happens when they do the math. Yeah, he just do it there. 24, negative 18. All right. Let's see about C. Now, I kind of wish they hadn't done the work for you here. You didn't have to do it this way. You could have done vector U dotted with twice V. That would have been fine too. Or pull the 2 on the outside. This is kind of like your association, but in reverse. Pull it on the outside and do it that way. Okay? Either way, let's do it the first way here. What is vector u? 2, negative 2. Oops. And dot that with twice v. What's twice v? 10, 16. And then let's do the math on that, the dot product, and what you get? 20.
Plus,
32, and that gives us negative 12. Okay? Let's do it this way. Let's do twice the dot product of u and v. Well, we just did the dot product of u and v, didn't we? That's right up here, negative 6. And what does that give us? Negative 12. Perfect. Same way. Okay, same answer either way. Now, I bet you they just do it that second way. Let's see. Yeah, that's all they did. 2 times the dot product that we had already done, and that gives you negative 12. But I wanted to show you that does give it the other way as well. Okay? Let's go to D. D is the magnitude of W squared. Okay? Let's first do that. What is the magnitude of W? Say again? Yes, it is. Okay. It's 16 plus 9 is 25. Square root of that is 5. Okay. And then you square that and you get 25. Okay, let's see what you get if you do W dotted with itself. Okay. This would be anybody? 16, which is 25. Yes, same result. And it better be. That's what our definition or properties or whatever we called it said it would be. Okay, let's see if they have an E. Oh, see how they did it? 25, same thing we did. Okay. Notice that the result of part B, we've already noticed that is a vector quantity, whereas the results of the other 3 parts are scalar quantities. And the reason is this is a scalar multiplied by a vector. That's a scalar multiplication, and that results in a vector. The other, that one, and this one, obviously are just dot products, which have to be scalar quantities. Okay. Any questions? Now, this leads, wait a minute, we haven't even talked about an angle at all, have we? Okay, don't believe so. So here, they're going to talk about it. The angle between 2 non-zero vectors, they better be non-zero vectors. How in the world could you have an angle between a zero vector and anything else? Zero vector has no directions. Between 2 non-zero vectors is the angle theta, as long as that theta is between 0 and pi. Okay? In other words, we don't talk about angle theta being all the way around like this. That's greater than pi. So we always talk about, it's not necessarily an acute angle, it could be obtuse, okay? Even an acute or an obtuse angle, but not a angle greater than pi. So that's got to be that, between their respective standard position vectors. Now, notice the equality here means U and V could be in the same direction, meaning the angle is 0, or they could be in exactly opposite direction, meaning the angle is pi. Okay, so both of those are okay. You just can't go beyond pi. So the angle between these, between their respective standard position vectors, I'm not really sure why they said their respective standard position vectors. Those, oh, okay, I see what they mean. Here's vector V. Count this as the origin, there's vector V here, and there's vector U there. Okay, that's what I mean. Okay, the next there shows how to find that angle using the dot product. Now this almost feels like you're going in an awkward direction, almost as if you're going to go in a circle. I'll tell you why, I don't know. There are two different definitions for a dot product. We just had one, the product, the sum of the product of their components. Sum of the products of their components. Okay? Now, there is another definition of a dot product, and let's see if they give it to us now. They don't quite, but they show you how you get the angle between two vectors. And they just pull this out of the air or some unknown body part. Okay? If theta is the angle between two non-zero vectors u and v, where theta is between 0 and pi, then the cosine of that angle theta is the dot product divided by the product of their magnitudes. Okay? Now, if these are parallel vectors, then, let me get this right first. Just leave it alone. That's your definition. What I meant by, and I think I will go on and describe this to you. When I was learning way back when, decades ago, what a dot product was, I think this is the first definition they gave us. U dot V is equal to the magnitude of U times the magnitude of V times the cosine of the angle in between, which is exactly what you would get if you multiply both sides of the equation like this. Okay? That's why I said there's a second definition for dot product. We had the first one, the sum of the products of the various components. Okay? Here's the second definition. Okay? They're not giving it this way. They're saying this is how you get the angle. Without really any justification, they just say, here's how you do it. They say, note here that because magnitude of U and magnitude of V are always positive, of course they are, then U dot V and cosine will have the same sign. Now here's what that implies, okay? This is always positive, so these two have to have the same sign. If theta is acute, that means U dot V is going to be positive because the cosine of acute angle is positive. If theta is obtuse, cosine in the second quadrant is negative. So therefore, the dot product of two obtuse vectors has to be negative because the cosine is negative, because that denominator is always positive. Okay. And that's why we don't let it go into the other two quadrants. Okay. We keep it in first two quadrants. All right. So, this is what I was starting to say, so I'm glad I didn't try to wave my arms and say it. This figure shows two possible orientations of two vectors. No, the possible orientation. I was going to say this is a lot more than two. Okay. When they're in exactly opposite directions of each other, the the angle here is theta, which is pi. Theta is exactly equal to pi. Well, cosine of pi is -1, okay? And the magnitude of this one, that's right, the dot product of those two divided by the product of the magnitude would then be -1, okay? Meaning the dot product of these two would have to be a negative number. Okay, we'll get there later. Okay, what if you're not quite to pi, but somewhere in that second quadrant, then you're between pi halves and pi. We're not going to count pi halves or pi here, okay? Well, the they've done a rather strange thing here. I wish I hadn't done it this way. I think I would have started on this side and gone this way. That would have made a lot more sense than going this way. Because you know you're in the second quadrant, theta, the cosine of theta has to be negative. Okay? It can't be as much as -1 because that was at negative at pi. And it can't be as much as 0, and this is why I wish they'd have started here and gone this way, because they're just telling you the cosine. I didn't like what I was saying. Come on back. Okay, here we go. The cosine of pi halves is 0. Okay? Cosine of all the half pi's is 0. So that's 0. We knew that, and the cosine of pi is -1. So therefore, if you're between pi halves and pi, you know the cosine has to be negative, so you know the cosine is between -1 and 0. Okay? So only negative values cosine can have. It's equal this at pi, and it's equal that at pi halves. So to be negative, it's going to be, and not -1, it's going to be there. Sort of a strange way to do this. Anyway, now, because of our earlier definition, we know that the dot product of two perpendicular vectors, because the angle here is pi halves, cosine of pi halves is 0. Okay? We know that. So this then tells us any two perpendicular vectors, the dot product is going to be 0. Okay? Now, if theta is acute, that means it's in the first quadrant, all the trig functions, including cosine, are positive, therefore cosine has to be between 0 and 1. Because we're saying theta is between 0 and pi halves. It can't be 0 and can't be pi halves. In between that, then you're going to have a positive that. If, however, they're in the same direction, the theta is 0, cosine of theta, cosine of 0 is 1, that's the only option. Okay? Cosine is going to be this, so your dot product is going to be, certainly jumping into this, but it is, because that cosine is 1, magnitude of this times the magnitude of that. They haven't gotten there yet, but that is going to be what the case is. Here is the magnitude of this times plus the magnitude of this with a minus the opposite. Okay. From theorem 11.5 that we just had, you can see that two non-zero vectors meeting at right angles, if and only if the dot product is 0. Such two vectors are said to be orthogonal, right angle, perpendicular. You can call them anything you want. Quite often with vectors they'll say orthogonal. So here's the definition of orthogonal vectors, just taking that and twisting it. If two vectors u and v are orthogonal, if and only if their dot product is 0. Same thing as here, but they're orthogonal if the dot product or when the dot product is 0. So that's where, however they're oriented in the plane, that will work. All right, so let's do example 2. That was all 771. And the top of 772, let's do example 2. This is also found at larsoncalculus.com. You can see an interactive version of this type of example. So here's U. 3, -1, 2. V is -4, 0, 2. And W is 1, -1, -2. And Z is 2, 0, -1. Okay, find the angle between each pair of vectors, U and V. So what would be that angle? How would you approach it? Second? Okay. Okay, we certainly can of each one. Is that what you're saying? We're going to need that anyway, so let's just do those up here. The magnitude of U is going to be what? Okay, 9 plus 1 is 10 plus 4 is 14, square root of 14. Very well done. Magnitude of V square root of 20. Now, 14, you can't reduce any. This, if you wanted to, so whether you want to or not, this would be 2 root 5. Is that what you said? Somebody?
I said square root 4, square root 5.
Yeah, which is 2 root 5. Got it. Okay. W, magnitude of W would be square root of 6. Yeah. Okay. And let's do Z over here. Magnitude of Z, square root of 5. All right, good deal. Everybody agree? So you're going to need those at some point, so let's go on and get them out of the way. So, how would you find the angle between U and V? Okay, let's do the dot product of U and V. -12 plus 0. Okay. Plus 4. That gives us -8. So there's the dot product of U and V.
And then you have to multiply the magnitude of U and V. So the
Okay.
14 times root 2 root 5.
Okay. So 5 times 14 is 70. So 2 root 70. Is that right? And I don't think you can reduce that any because that's 2 times 5 times 7. No, nothing you can do there. All right.
So that would be
You've got all the pieces in place. What do we do with the pieces?
on the cosine.
Say again? Okay. What's the cosine? The cosine of this angle, what do you want to name it? Theta? Oh, one of my favorites. Okay, is equal to? Over 2 root 70. I can simplify that a little bit to make it -4 over root 70. Now, What's one thing to always check? Because it'll be a real good indication of whether you've made a really serious error or not. What is cosine always between? -1 and 1. Do you think that's going to be the case here? 4 would be the same as square root of 16, right? And 16 over 70 is certainly going to be between 0 and 1. And this is actually between -1 and 0. So that seems good. Now, what do we do now? That's just giving me the cosine of the angle. I want to know what the angle is. Arc cosine, or inverse cosine. So theta is equal to the inverse cosine of -4 over root 70. Oh, my writing's terrible. Okay. Pull out your handy dandy calculators. I'm not about to do that one in my head. I can't. Okay. Okay, I take it you're in radian mode. No, it's fine. I'll just say that sounds like a radian answer to me. Doesn't it to you?
Yeah, I think it's in radian.
Huh?
It's in radian mode.
Okay. The reason for that, if that were degrees, you'd been in the first quadrant, and that's not negative in the first quadrant. So you've got to be in the second quadrant, and 2 radians and some odd is in the second quadrant. Now let's see what they did. And they left, what did you say your answer was?
2.07.
They did 2.069.
Yes.
So 2.069. And they write radians after it, which is okay. The thing is, rads is not a unit. It's a ratio. But that's okay. If you leave off the degree sign, that indicates radians. Okay. There's the angle between those two. How about the next two?
So the cosine theta.
Okay, going right for the juggler here. So cosine theta is equal to U dot W over magnitude of U times the magnitude of W. All right, I'm really cramped here. What does that give you? What's the dot product of U and W? 3
plus 3 plus 1.
All right.
And minus 4.
Ooh. Over. My question is, who cares? Why? Gonna be 0. Okay. What does that tell us?
So the angle will be pi halves.
Absolutely. Theta has to be pi halves. Remember, it's got to be between 0 and pi. That's the only place where the thing is 0. So, thank you. An easy one. Okay. Let's do this one over here so it won't be quite as crowded. Okay, well, what are we looking for? Okay, so we're looking for, you want to start with the angle or cosine of the angle? Or are you going to start this one?
Start with the cosine.
With the cosine? Okay, we'll do that. You could start with the angle and just do an inverse cosine and go from there, but that's okay. Cosine theta is equal to
The dot product of V and Z.
which would be
Negative 8
-8
Plus 0 minus 2.
minus 2. Okay, over root 20 times root 5. Is that what we said? Okay. I think I know what that's coming out to be. What's negative 8? Oh, minus 8 minus 2. Negative 10. And what is the denominator? It's square root of 100, which is 10. Okay. So this is negative 1. What does that imply? Yes, theta is pi. 3.14. 1, 6, blah, 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 blah. Okay, let's see what they got. The second theta was pi halves, absolutely, and the third theta was pi. Theta was phi. Okay, never mind. All right, now, finally they get around to doing what I said earlier. Let's see if they're going to give that on the slide. Oh, let's see how they did it. Okay. Had to have done about like we did. Okay, first they started with that formula. Cosine theta is u dot v. How are we doing on time, by the way? 1 minute. Okay, quickly. U dot v over magnitude of u times v, and that gave us minus 8 over, wow, thank you for doing it that way. Okay. Negative 4 over root 70, exactly like we got, and that gave us exactly what you got, 2.069 radians. Second quadrant, by the way, because it's negative. Okay, the next one, real quickly, you got 0 over whatever, and that told you that the angle had to be pi halves. And the third one gave us negative 10 over 10, which is negative 1. That told you you had to be at pi. Notice that V and Z are parallel. We didn't notice that before, did we? We weren't paying attention, were we? They separate them like crazy. V and Z, yeah. Negative 2 times this is exactly that. Yeah. So we could have told that without doing anything else, that those are like that. Okay. Now, we will start next time with what I already told you, but I won't count it against you. Bottom of page 772. Let's get a few homework exercises here. I've got to bring in my better eraser. Okay. All right, you can do any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. You can do any of the odds 11 through 17. They're all at Calc Chat. 13's at Calc View. We'll pick up and do the rest of those next time. Good deal. All right. See one of you tomorrow, and the rest of you have a good weekend. You can still have a good weekend, but I won't see you tomorrow.
So you keep specifying that Dawson's in your class.
What's that?
You keep specifying that Dawson's in your class.
Yeah. All right. Good deal. We'll